Hey everyone, so today we're going to build a toolkit, but not with hammers and wrenches. No, we're building a mental toolkit for figuring out the odds of everyday life. We're going to master two of the most powerful words in probability, and or. I mean, think about your own day, right? Life is almost never about just one single thing happening. It's always a combination. What are the odds you'll hit traffic and be late for work? Or what's the probability you'll land this job offer or that other one? These are the kinds of questions we're going to tackle. So here's our game plan. First, we'll get the basics of ands and ors down. Then we'll dig into the and rule and a really crucial distinction that comes with it. After that, we'll add the or rule to our kit, look at a special case, and then put all our new tools to work. All right, first things first. What actually happens when you take a couple of simple, separate chances and smush them together? Well, you get what we call a compound event. It's a fancy-sounding name for a really simple idea. It's just an outcome that depends on two or more things happening. Flipping a coin? That's a simple event. Rolling a die? Another simple event. But wanting to know the chances of getting heads and rolling a six? That combo? That's a compound event. Okay, time to grab our first major tool from the box. This is the one you'll reach for whenever you need to know the odds of multiple things happening together, when you need this outcome and that outcome. The keyword to listen for, the one that should set off alarm bells in your head, is and. The second you're trying to figure out the probability of event A and event B, you should immediately think multiply. But there's a little wrinkle we need to iron out first. And here's that wrinkle. It's a critical question you have to ask yourself before you start multiplying anything. Does what happened in the first event have any effect at all on the chances of the second event? Because the answer to that question completely changes how we do the math. This brings us to this absolutely vital distinction between what we call independent and dependent events. Getting this right is so important, whether you're, pricing insurance policies or trying to diagnose a patient. You've got to know if your events are linked. Let's start with the easy ones, independent events. This is when the outcome of one thing has absolutely zero impact on the outcome of the other. For these, the formula is as simple as it gets. The probability of A and B both happening is just the probability of A times the probability of B. That's it. The classic example is flipping a coin twice. Let's say you get heads on the first flip. What are the odds of getting heads on the second flip? Still 1/2. The coin doesn't have a memory. It doesn't pair what happened before. So to find the odds of getting heads and then heads again, we just multiply 1/2 times 1/2, which gives us 1/4. But what if the first event does change things? Well, then we have dependent events, and our formula gets a little tweak. We still multiply, but it's the probability of A times the probability of B, given that A has already happened. That little vertical line in P of B pipe A, it just means given. Let's make this crystal clear. Imagine you've got this bag of marbles. We're going to draw one out, and here is the most important part of this example. We are not going to put it back. On our first draw, the probability of grabbing a red marble is pretty straightforward, right? There are 5 red ones in there out of 8 total marbles, so our probability is 5 out of 8. No problem. But look, because we didn't put that red marble back, the whole situation has changed. The universe inside that bag is different now. We're down to only 7 marbles total, and only 4 of them are red. Our first action permanently altered the state of play. So if we want to know the probability of drawing a blue marble now, it's not 3 out of 8 anymore. It's 3 out of 7. The outcome of our second draw was completely, totally dependent on what happened in the first draw. And that right there is dependency in a nutshell. Okay, toolkit check. We've got our AND tool down. Let's put that aside and pick up our second big one, the addition rule. This is what you use when you want to find the probability of this happening or that happening. So just like AND means multiply, OR means add. The general rule says the probability of A or B happening is the probability of A plus the probability of B minus the probability of both A and B happening together. Now, why do we subtract that last part? It's just to make sure we don't accidentally double count the overlap where both things happen at once. But sometimes there is no overlap. Some events just plain can't happen at the same time. And this creates a really nice, simple special case for our OR tool. We call these mutually exclusive events. Think about rolling a single die. You can't roll a 2 and a 5 at the exact same time. It's physically impossible. For these kinds of events, the probability of them happening together is 0. And that simplifies our addition rule down to something beautiful. It's just the probability of A plus the probability of B. That's it. Okay, now this is the spot where a lot of us get tripped up. The terms independent and mutually exclusive can sound kind of similar, but they describe completely different relationships between events. So let's put them side by side and clear this up for good. This table breaks it all down. Mutually exclusive means the overlap is 0. They can't happen together. Independent means one event happening doesn't affect the other. But here's the real mind bender. Mutually exclusive events are actually highly dependent. Think about it. If I roll a die and I tell you I got a 2, you know with 100% certainty that I did not get a 5. The outcome of the first event gave you complete information about the other. All right, our toolkit is officially assembled. We have our AND multiplication rule for both independent and dependent events, and we have our OR addition rule for both overlapping and mutually exclusive events. Let's take it for a spin. Let's look at a student who's picking courses. We know a few things. The probability they take algebra is 0.3. The probability they take biology is 0.7. And the probability they take algebra, given that we know they're already taking biology, is 0.4. Okay, let's use our toolkit. First, what's the chance they take both? Well, both is an AND question, so we multiply the probability of algebra given biology, which is 0.4, times the probability of biology, 0.7. That gives us 0.28. Second, the chance they take either course. Either is an OR question. We add their probabilities and subtract the overlap we just found. 0.3 plus 0.7 minus 0.28 equals 0.72. Third, are these events independent? Well, the probability of taking algebra is 0.3, but if we know the student is taking biology, that probability jumps to 0.4. Since those numbers aren't the same, nope, they're dependent. And finally, are they mutually exclusive? Well, we already found the chance of taking both is 0.28. Since that's not 0, they are definitely not mutually exclusive. And that's really what this is all about. This isn't just about formulas on a screen. It's about having a logical framework, a real way to think clearly about a world that is filled with uncertainty. So as you go about the rest of your day, just pay attention to your own thoughts. You're constantly using this toolkit without even realizing it. Should I leave for my appointment now or in 10 minutes? What are the chances I can get this errand done and make it home for dinner? Now you have the language and the rules to understand what your brain is doing instinctively. So the only question left is, how many times have you already used this today?